Hi everyone, this is a re-recording of my second capstone. I chose to do regression analysis on a synthetic dataset that was about medical costs, medical charges, based on other variables like age, sex, number of children, etc. And first we're going to describe the data, then do some pre-processing, and then apply several regression models, and then choose the best. So after loading the libraries and loading the data, some basic descriptive statistics show us that there's a large disparate ranges between the different numerical variables. So that tells us that we're going to need to normalize or scale them before using them in the regression analyses. Then for the EDA, we checked, and thankfully there was no missing data. The distribution of the target variable shows that it's not normal. So we're going to have to also revisit that. Do we want to assume it's normal and go ahead and carry out regression because regression assumes normality? Or do we want to apply some transformation to it before using it? For the categorical variables, we had sex, whether they were a smoker, and their region. Sex and region were pretty evenly split. Smoker was less than a quarter of the population. Unfortunately, regression models can't use categorical variables, so we had to do some encoding. I chose dummy encoding because there was only a couple features. I did ones and zeros for sex and ones and zero for smoker and 0 to 3 for region. So here you can see them side by side. The southwest was a 1, southeast was a 0, northwest was a 2, female 0, male 1, etc. And then I dropped all the categorical variables. So now we have all numbers, which is good. We could also have used label encoding, which was also similar. One hot encoding added too many additional columns to the data that we didn't really need. So this was the simplest way. For preliminary relationships between variables, on this heat map, the only one that stands out to us is the charges smoker relationship at 79%. Everything else is pretty low. Looking at pair plots, it's the same thing. There's no clear trend that we can identify. Adding regression lines to the pair plots to visualize any potential relationships. It's a lot of noise. So we're just going to stick with smoking and do some more analysis on it. The distribution of charges for smokers was bimodal. It wasn't straightly normal or linear. And then the distribution of the costs for non-smokers looked just like the distribution for the entire population, which makes sense because they were the majority. So we're going to carry out feature engineering because we see that we have to. The method we choose would depend on how many outliers we have, because some of them are more sensitive to outliers than others. Excuse me. Standard scalar, for example, assumes the normal distribution. So looking at the outliers, we decided. First, we tried z-score scaling, standard scaling, which didn't work. I mean, it worked, as in it gave numbers, but it didn't work in the models because it didn't fit. Same with partial normalization, where only the features were normalized and not the target variable. That also didn't work because the target was going to skew all the data. So I used robust scalar with a logarithmic transformation of the target variable. So that way, we have values that don't look so disparate, because I don't know if you remember at the top, there was a large disparity between the values in the different columns. Now going to the modeling, I wanted to do as many models as possible, so I chose 10, and I tested it with one, first of all, SVR, to see if we would get a good R score, and 86% was okay. So I went ahead and put all of them in a function so it would just loop through and give us the R results and the mean squared errors. So here were the results. ElasticNet had the highest mean squared error. AdaBoost had the lowest R squared. I mean, Lasso Regression had the lowest R squared, excuse me. ElasticNet also had a low R squared. But gradient boosting had pretty good results for both of them. So it had the lowest MSE and the highest R squared. So that means that we're going to go ahead and choose that as our model for this data set because it shows that it has better predictive performance. Thank you.